This is the Kybalion and Physics Part 3, Giant Atoms. It's one of my favorites. So far we've talked about dark energy. I've defined it as being the direct opposite of outward moving light. The term inward parts has been coined to be the measurement of the tiniest parts of dark energy. Instead of electrons, it's inward parts. We've also talked about gravity as being the relationship between different sized atoms. And if you missed all that, please watch part 1 and 2, because we're not going backwards. We're going to plug ahead. I'd like to show you two examples of celestial bodies that are actually giant atoms and why. So here it is. Giant atoms. Let's start with the Sun. The Sun is the largest celestial body in our solar system. All the major planets in our solar system revolve around the Sun. The Sun is a star which emits an enormous amount of heat and light. It is already known that stars can be any size. In fact, there are stars that dwarf the size of our entire solar system. Amazing, right? Currently, it is believed that the Sun is a hydrogen reactor or even a giant ball of gas. But based on what we know from watching hydrogen bombs or gas explode, the Sun would have exploded upon ignition. Also, the current studies of the Sun tend to ignore the darkness we can observe in sunspots. Sunspots reveal the dark energy beneath the surface of the Sun. There is absolute darkness beneath the brightest object in our sky. And I find this very interesting because when you look at models of the Sun of how they work on the inside, they don't mention sunspots or the darkness underneath the brightness of the Sun. NASA spots giant hole over the Sun. That was the headline from the American Fox News channel on July 30th, 2013, as reported by NASA. This is the image that was reported to show a hole in the Sun. And this is my artistic version of it for the book. But it actually showed the dark inward energy underneath the brightness of the Sun. If space were somehow gray, we would see that the darkness underneath the surface of the Sun is still dark. The Sun is a giant atom. Yes, it is. The Sun's nucleus would be billions of times bigger than an atom's. How large it is a math problem. And by a giant atom, I do mean one nucleus, as explained in the previous two videos. The massive amounts of inward parts a star has do not crush the nucleus because masculine and feminine energy come together to create, not destroy. Although it does not appear to be spinning fast, the Sun also travels a great distance around the galactic center. The outward motion of spinning and traveling causes the inward energy to be pulled outward as explained by centrifugal force. Centrifugal force is when an object is spun, it gets pulled outward. Spinning causes an outward force. The outward force caused by spinning can be observed in centrifuge machines and can be felt by spinning around really fast with your arms outstretched, which actually becomes very painful. Inward energy gets pulled outward by centrifugal force. How fast it needs to spin to be pulled outward, again, is a math problem. The faster the spin, the stronger the outward force is. Therefore, stars that spin faster produce more light. An example, neutron stars. Eventually, centrifugal force will break down the enormous atoms, which would then release all the excited heat and light within the nucleus. This does mean that the Sun was bigger when it first ignited and has slowly shrunk over time. Currently, quantum physics has labeled a neutron star as a tiny star, about the size of a school bus, that shines brighter than larger stars, like our Sun. A supernova is described as the death of a star, releasing all outward forces in a massive explosion. Stars are giant atoms that spin and travel fast enough to ignite, getting smaller until they completely combust. The birth of stars is discussed in part 7 of this project. The Sun, our star, is on the outside of the galaxy. It has a very wide orbit around the galactic center. This incredibly long orbit plus the spin is enough outward movement to pull the dark inward energy into outward energy, which is the cause of every star's brightness. Stars orbit their galactic center the same way planets orbit stars, as above, so below. At the center of every galaxy is an even larger celestial body. The first image of a black hole was created in 1979 by the artist Jean-Pierre Lumière. He used an early transistor computer to plot the stars, and then he drew the dots. It most certainly looks like a gargantuan black body, an incredibly large atom surrounded by many stars. This is a recreation of Mr. Lumière's drawing, but his is far more spectacular. A galaxy is a collection of stars swirling around an even bigger celestial body. The fact that stars spin and orbit around the galactic center would imply that there is something in the middle of each galaxy with an even bigger nucleus of light than what stars have. It has been labeled a black hole. A black hole, like the sun, is an even larger atom. It is the largest atom in a galaxy that all stars rotate around. It is not moving fast enough to ignite, so it stays in its primordial state, a black body. Here's an interesting side note. It turns out that I'm not the only one that believes that these black holes are giant spherical objects. Artists working for NASA and the National Geographic have been putting out work that show that these objects are giant spherical objects, giant black bodies, not holes, not two-dimensional holes. There's no time travel, and we'll get to that in part 6, where I will be debunking quantum physics. But there it is. Check it out for yourself. The artwork is beautiful, actually. In order to understand why black holes suck in heat and light, we first must understand what the electromagnetic field is, which I call balancing energy, and you'll understand why. And that's going to be part 4, balancing energy. So stick around. Thank you so much for watching.